Hello there. In this video, we're going to briefly discuss some basics associated to bivariate data. So bivariate data is usually ones that come in the form of ordered pairs, say x, y, where x comes from a set and y comes from another set. Say you want to sort of, investigate the relationship between pressure and temperature, for example. And let us assume that there are n values in the sample, so n ordered pairs. So of course, when you graph this, you're going to get some relationship similar to the following, namely something like this. So in this video, we're just going to talk about some basics associated with bivariate data and also some formulas associated with it. Let's start with some basics that all of us should be familiar with at this stage. So since we have a set of x values and y values, we should be able to easily calculate each of those corresponding means. Namely, x bar is defined to be equal to 1 over n times the sum from k is equal to 1 to n of all our x values, and the average of y is defined to be equal to 1 over m times the sum from k is equal to 1 to n of y sub k. And keep in mind, there has to be the same amount of x values and y values, and if you don't, then you have to sort of do some cleaning for your data. So also, we have two formulas, namely the sum of squared differences for my x values, which is going to be the sum from k is equal to 1 to n of our x values minus the mean, the quantity squared, and the sum of the squared differences of our y values is going to be equal to the sum from k is equal to 1 to m of yk minus the average of y squared. So from here, we can define our variance. So the variance of x is going to be equal to the sum of the squared differences of x divided by m minus 1. And the variance of y is going to be equal to the sum of the squared differences of y divided by m minus 1. And finally, the standard deviation of x is going to be equal to the square root of the variance of x, and the standard deviation of y is going to be equal to the square root of the variance of y. So these are just some basic formulas that now are going to be useful to us. So now we define a new measurement that only applies to bivariate data, and that is what we call the covariance. So the covariance. So the covariance between two sets, x and y, is going to be defined to be equal to 1 divided by m minus 1 times the sum from k is equal to 1 to n of xk minus x bar times yk minus y bar. So this is the sum of the products of the corresponding differences between x and y values. So let's do a basic example to sort of illustrate how to calculate this. So let's assume I have a sample set of points, 1, 2, 3, 4, and 5, 6. So if this is the case, then that means the size of my sample is 3, not 6. So our x values in this case are going to be the points 1, 3, and 5. So it's easy to see that x bar is going to be equal to 3. And our y value is going to consist of 2, 4, and 6. And it's obvious that y bar is going to be equal to 4. So I've chosen just numbers to sort of illustrate the idea. All right, so therefore, the covariance between x and y, or the covariance of s, is going to be equal to the sum from k is equal to 1 to 3 of xk minus x bar times yk minus y bar, all divided by m minus 1, or 3 minus 1. So let's just map that out. So it's the sum of the products. So let's start with the first one. So that's going to be equal to 1 minus the mean of x, and then 2 minus the mean of y, plus, now let's look at the next value. So now we have 3 minus 3 times 4 minus the mean, then plus, so the last one. So it's going to be 5 minus the mean of x, and then 6 minus the mean of y, all divided by 3 minus 1. So that's going to be equal to negative 2 times negative 2 plus 0 times 0 plus 2 times 2, all over 2. So that's going to be 4 plus 0 plus 4 over 2, which is 8 over 2, which is 4. So therefore, the covariance of our sample is equal to 4. And that's how you calculate the covariance between two sets. So a couple properties that are associated to this covariance and also how to interpret it are the following. So properties. So the covariance is unbounded in general for any set S. So it's possible to have a covariance of 50, 5 million, negative 5 trillion, and so on. Now another property is associated to the graphs, and I will draw two possible, or there's actually more scenarios than this, but let's assume we have these type of scenarios. So let's assume we have that, and we have something like this. So if the data seems to be, positively correlated, typically this is going to imply that the covariance of S is going to be a positive number. And if the data set seems to be negatively correlated, typically the covariance of that data set is going to be negative. So positive covariance typically refers to positive correlation, and negative covariance typically refers to as negative correlated data. Now there's another number aside covariance that is used to describe these types of things, and it's what people refer to as, some people call it the Pearson correlation coefficient, or just the correlation coefficient. So recall, we usually have some sample that is drawn from a population P. So the correlation coefficient for the sample is typically denoted by R, and the correlation coefficient for a population is typically referred to by the Greek letter rho. So this is Greek letter rho. So that means R is an approximation for rho, where R is a statistic and P is a parameter. So to calculate the correlation coefficient, the definition is R is equal to the covariance of our sample between X and Y divided by the product of the standard deviations of X and Y. And similarly, rho is going to be equal to the covariance of the population between X and Y values divided by the standard deviation of X and the standard deviation of Y multiplied together. So these are the formulas for R and rho. And if you're using Excel, for example, you can calculate that by Pearson, select the X values, select the Y values. And that can be used to calculate this value for both. And a very important property for this is that R is always between -1 and +1. And this is for all samples and populations. So this is a very useful property to have. So let's consider a variety of cases. So let's look at the entire spectrum of R values. So let's look at, say, -1, 1, 0, -1/2, 1/2, and all in between. So if the R value is -1, one can prove that, yes, the data is negatively correlated, but all of the points will lie on a line. Similarly, if you have a correlation coefficient of +1, then all of the values will be positively correlated, and all of the values will lie on a line. If you have something like 0, then you should not see any pattern whatsoever. It should be, a little bit more scattered. Now, if you're at points in between -1, 0, and 1, then you may see some correlation, like it might be slightly negative or it might be slightly positive, but there might be some variation amongst the x and y values. So it's important to know the closer r is to plus or minus 1. So if absolute value of r is approximately equal to 1, then the data is likely to be linearly correlated. And I use the word likely here because there are definitely some small exceptions to this rule. And also, if the absolute value of r is not close to 1, that does not necessarily mean that it's not linearly correlated. But if the absolute value of r is exactly equal to 1, then the data is linearly correlated. We'll investigate this likely portion a little bit later. So another thing that is typically discussed in some basic bivariate analysis is what we call the line of best fit. Some people also refer to this as the least squares line or the linear regression line. These are two alternative names for this. And pretty much what the line of best fit does is it takes your data, your bivariate data x and y. So let's assume this is the x-axis and let's assume this is the y-axis. So it pretty much best fits this data and pretty much describes this data in some way. And I'm going to call this y hat is equal to mx plus b. So there's two parameters, m and b, that uniquely decides this line that best fits the data. So I'm not going to derive these formulas and where they come from. We sort of give a informal proof later on. But the slope of the line of best fit can be calculated by first calculating the covariance between your data sets and dividing by the variance of your x-coordinate. So that gives you the slope of the line of best fit. And the y-intercept can be found by doing the average of y minus the m value times the average of x. So that will give you that value. So what can this line of best fit be used for? So let's assume we have a data set that appears to be positively correlated. And also let's assume that this set is, say, bounded between two numbers, say x is equal to a and x is equal to b. So I'm going to assume this is the x-axis and this is the y-axis. So let's assume we have this line of best fit, which I'm going to highlight in yellow. So y is equal to mx plus b. So if you use this line to, say, guess a point, say here, this is what we call extrapolation. So if you want to, say, have the gas prices in January and the gas prices in April, using that line of best fit to sort of approximate the values at February or March would be an example of extrapolation. Now, if you only have data, say, for the month of January and you sort of want to see what it may be in the month of February, say over here, then this is what we usually refer to as prediction. And if you want to sort of figure out what was going on in the past, some people refer to this as retrodiction. Now, in general, extrapolation is the most reliable scenario for approximations because you have the majority of the data located around the value for which you are approximating, whereas for the prediction and retrodiction sides, you're sort of assuming that the data sort of continues in that trend because even though it's increasing generally on the interval AB, it definitely is possible that it could begin to, say, decrease. So instead of being up here, it could sort of go downwards, or it could have gone that way on that side. So using it to sort of predict and retrodict things definitely comes with some assumptions, but in future videos when we have some basic hypothesis testing and confidence intervals, we can use those to sort of dictate, how confident are we that this trend will likely to continue to occur past these intervals of knowledge. So this is just a basic outline of bivariate data and some of these things that we use for analyzing bivariate data. But again, we're going to revisit these things later when we focus more on linear regression and nonlinear regression analysis. Hope you enjoyed.